Welcome back. In the previous lecture, we had proved the open mapping theorem for a linear bounded operator, and as a consequence, we had established the stability of a two-point boundary value problem. In this lecture, we are going to prove the open mapping theorem in the nonlinear situation, that is, we will do in the finite dimensional situations. Okay, so we will not have the linearity assumption that we had previous time, and as a compromise, we are going to restrict ourselves to the finite dimension. So, if you recall, so far what we have done, even from the first lecture when we started doing the fundamental theorem of algebra, it was trying to solve some equation, find the roots of an equation or solutions to some equation, right? ODE, whatever ordinary differential equation that we have seen, trying to prove existence of solutions, everything. Similarly, the linear algebra, which is which is a kind of linear system of equations, and so on, right? So, every mathematical modeling usually can be reduced to a question of trying to solve an equation of the form. So, f is given, p is given. Can you find all x such that f of x is p? Right? This is how usually we deal in mathematics equations where we have knowns and unknowns. We need to find the unknown using the known property. Right? So, in particular, if this f was a linear map, say from Rn to Rm, and then this question of solving for x where p and f are given, f of x equal to p, if you want to solve this equation, is same as solving the matrix equation or the system of linear equation where A is the matrix corresponding to the map F here, right, which will be now an M cross N matrix, right. So solving this equation is solving this matrix equation or the system of linear equations, right. And this problem has a unique solution whenever the matrix is an invertible square matrix and so on. That is when m is equal to n and it's invertible. So then the solution x is given as A inverse of P, right? So then you have any solution. You also have situations of many solutions, no solutions, and so on. This is what you do in the course of linear algebra, right? So now just see this same thing in a very different perspective. So look at that. If A is the matrix corresponding to the map F, and F is a map from Rn to Rm, that means this map F takes an n vector and gives us an m vector. That means this F has components, m components. So let's call those components as Fi. So each Fi, if A is a matrix corresponding to F, is actually A acting on X, right? So the ith component of Ax is Fi. So the ith component of Ax is precisely this. So Fi is this this sum, right? For where this I is the fixed one and the sum is over J. So this is fine. So now if suppose f was a function which admits first order partial derivatives, right? Then when we say that we have a unique solution when A is an invertible square matrix, so the invertibility of A here is same as the invertibility of the Jacobian matrix, right? Jacobian matrix corresponding to F, which is JF, which is this, which and that matrix is DJFI, because if these are the partial derivatives, if DJFI are the jth partial derivative of Fi, so you have the matrix, and that which is df by dxj, which is precisely, if we differentiate here with respect to the j variable, what we get is aij. So this matrix A that you have here is precisely the Jacobian matrix, right? And so the invertibility of A is the invertibility of the Jacobian matrix if F admits partial derivatives, right? So to solve an equation of the form fx equal to p whenever f is non-linear. So here you see when what we do in linear algebra is the linear situation, right? So when this f is not a when this f is not a when this f is not a linear map, then what you do is you do a linear approximation of this function, right? So if f is a differentiable function and so on, so if you do a linear approximation, then then fx, so this is just the truncation of the generalized Taylor series up to first order derivatives, right? So this is the linear approximation of this function, right? This is a tangent plane, right? So approximating this function by its corresponding tangent plane at the point A. So this is the approximation of f at the point A. So f has this linear approximation. So if I want to solve this for a non-linear thing, we basically approximate f by its so we basically take the linear approximation of the f and then try to do what we know from the linear theory, right? So if we want to solve this equation, we want to, as we seen here, the Jacobian has to be invertible. So if we want to solve that equation, then we expect that f should admit a local inverse if the linear approximation is invertible, right? So this is the linear approximation, and linear approximation being invertible basically means that this derivative of f is invertible, right? And this is what uh, is the inverse function theorem, which is something that we will see in the next lecture. Okay, so we are so whatever we are saying here is related to uh, whatever we know from the linear theory, whether we can carry over the results to the nonlinear situation. Not always, not exactly, but in some situations you can do some carryover, but that again is not global but local. That's why I put a local word here, right? So the invertibility may not happen globally but may happen locally. So we can have local results here, right, in the nonlinear situation. That is how we handle the nonlinear theory. So the inverse function theorem is going to give you a necessary condition for solving equations of this form locally for a system of n nonlinear equations. So you have n nonlinear equation with n unknowns. Okay, so the m and n are same. Okay, so that's what we are going to develop in this lecture, in the next, and so this lecture and next lecture. Okay, so to begin, let's as we have already observed from the previous slide, solving this equation is related to the invertibility of the Jacobian matrix, right? And the invertibility of the Jacobian matrix basically means that uh, is related to whether the determinant is zero, non-zero, and so on, right? So let's look at the properties of non-zero Jacobian matrix. So this is a result for an open ball of radius r. Okay. So what is the statement? We have a ball. We have a ball centered at A of radius r in Rn, and del B is the boundary of the ball. So this is an open ball of radius r. The boundary of the ball is all those elements which is exactly of the radius, which is exactly r distance from A. It's a boundary. So B line B closure is the closure of this open ball. Okay, so this B is the closure of this open ball. Now we have a function f which is continuous function in B closure. It's an Rn value, it's a vector valued function, right? And all its partial derivatives exist for all x in B, right? So djfi x exists for all x in B. And the other condition, so third condition that we have is that f of x is not equal to f of a for all x on the boundary. So the value of f on at sort of all the boundary points is not same as the value of f at the center. Okay, and the Jacobian of f, which is that matrix which I wrote down, right? Jacobian of s, which is this matrix. The Jacobian of f at x is non-zero for all x in B. So whenever these four conditions are satisfied, then we say that f of B contains an open ball centered at Fa, right? So B is this open ball of radius r, right? F of B will be an some subset of Rn here, right? Some subset here, and what we claim is that under these conditions, f of B contains an open ball centered at f of A, right? Because A is the center of this ball, f of A is in f of B, so there is a open ball in the range of B. That's what we are going to prove. So to prove this, we start with this map G, which is defined on the boundary of the ball of radius r. What is it? It is nothing but the distance of basically the distance of the value of f at x. So g of x is mod f of x minus f of a, right? So g of a, which is sorry, g of a cannot be taken because this is map is defined for all x on the boundary, and we have already checked here that f of x is not equal to f of a for all x on the boundary. So this can never be 0. Okay, this is never equal from this assumption 3. So which means that g is always positive. It can never be 0. So it has to be strictly positive. So g is always positive because from the assumption 3, and g is continuous, right? Because f is continuous and its composition of f and mod, right? Both. So it's composition of two. So it's mod and f composition. So it's composition of two continuous functions. So g is continuous on the boundary of the ball. So G is a set defined on a compact set here. So the image is also going to be compact because it's a continuous image of a compact set. So G will achieve its minimum. It will achieve both maximum and minimum. We are interested in the minimum. So G will achieve its minimum M on some point of the domain, which is the boundary of the ball. Okay. So there is a minimum M for G, and that minimum will be achieved at some point here by G. Now what we are going to show is that if I take a ball of take a ball of radius m over 2 centered at f of a, that is the ball that we will show is contained in f of b. Okay, so U is the ball of radius m over 2 centered at f of a. We will show that this U is contained in f of b. Okay. So for that, we start with an element of U. So if I take a y in U, we need to show that y is actually in f of b for all y in U. So if y is in U, so which means that so we need to show that y is in f of b. That means we need to find an element in the ball of radius r such that the image of C under F is Y, right? If we show that, then we have shown this. That's what we need to show. So we now consider another function h, which is defined in the closed ball of radius r centered at A, which is defined as mod f of x minus y. Okay, so this y is the fixed y that we have chosen from U. So you take any x in this ball, you look at the image of x under f, okay, that will be in f of b closure, right? Now look at this difference f of x minus y. Y is some element of u. So now again, u is a continuous function by definition here, right? It's just f is continuous and it's just modulus of that. So h is a continuous function on B closure, and therefore it will attain its minimum at some point C in B closure, right? Because it's a compact set, continuous function, compact set on a compact set, so the range is compact as well. So there is a maximum and minimum, and they will be achieved. So there is some C in B bar such that HC is the minimum of H. Okay. Now look at what is HA. A is the center of this ball, right? H of A by definition is f of A minus y. Okay, but y was taken such that it's in U, and U is a ball of radius m over 2 centered at f of A. So if y belongs to this, y minus f of A is less than m over 2 by choice, right? By choice. Y is in U. So y minus f of A modulus is less than m over 2, right? Now h of C is the minimum over the entire B closure. So HA is one element, I mean A is one element of B closure. That means HC is actually less than HA, and HA is less than M over 2, which means H of C is less than M over 2. Now for every element on the boundary of this ball, of the ball of radius R, we take any x, and then we compute Hx, right? Because H is from the closure of B bar. So what happens to Hx when x is coming from the boundary of this ball? So h of x is f of x minus y by definition. Now a triangle inequality applied here, that is f of x minus f of a, right? You add and subtract y, and then which will be less than or equal to this plus this, and that's what we have used here, right? So f of x minus f of y is bigger than or equal to f of x minus f of a minus f of a minus y. Fine. But f of x minus f of a is precisely the g that we defined earlier. So g is precisely f of x minus f of a for all x on the boundary. And since x is on the boundary here, so f of x minus f of a is precisely g of x by definition of g. And f of a minus y is less than m over 2. So minus of that is greater than minus m over 2. So g of gx is greater than gx minus m over 2, right? But g has the minimum m, right? That's what we have seen earlier. G has the minimum m here on the boundary. So G has the minimum m. So this is greater than or equal to m minus m over 2, which is m over 2. So h of x is bigger than or equal to m over 2 for all x on the boundary. So for any x on the boundary of this ball, the value of for any x on the boundary of the ball, h takes the value which is bigger than m over 2. Okay. So hx is bigger than m over 2 for all x on the boundary. But we have already seen that HC is less than m over 2 for C, which means C cannot be on the boundary, which means C has to be in the interior. So C belongs to B and not on. Yeah, so C belongs to B and C does not lie on the boundary of B. Okay. Now, if C is a minimum of H, C is also minimum of H square, which is the square of this map, right? Pointwise product. So H square is again a map from B closer to 0 infinity, where H square is mod fx minus y whole square, which is precisely this, right? Using the modulus definition, right? This is a vector in Rn, right? Fx and y are vectors in Rn, so it's a Rn norm, Rn modulus. So this is so square of that is this. Okay, so h square is this. So, and we are already given that f is right. Our one of the assumption is that So far we have used the condition 3, we have used the condition 1. So far we have not used the condition 2 and 4, right? So now we are going to use the condition 2, which is that all the partial derivatives of f exist. So using the partial derivatives of f, we can so for each partial derivative, because c is the minimum, then the partial derivative of h square is 0 at c belongs to b, right? Because that's the critical point here, right? So if dj h square is 0, so you apply dj here. So you, since f can be, so the dj will go and apply on fi here. So if you differentiate this with respect to the jth component, jth variable, so what you have is 2 times this dj of fi evaluated at c, right? That is precisely this. The 2 can be removed because finally it's going to be equal to 0. So 2 times of something is 0, so that something is 0. Okay, so this is evaluated at c because that's what we know. dj h square of c is 0. So this is 0, but what is this? This is precisely, right, this matrix on this vector equal to 0, right? This is precisely this matrix evaluated for, I mean, operating on this vector. This equals to 0. Now, can we solve this? Yes, you can solve this if this is invertible, right? Right. So whenever C belongs to V, we are given the fourth condition that the Jacobian is non-zero, right? Which precisely means that this is invertible here, which means that Fc minus Y should be 0, which is Fc is equal to Y. And if Fc is equal to Y, means that Y is the image of C under F, which means Y belongs to F of B. But the Y originally we started with somewhere in U. So for any element of U, it's contained in Fp. So we have shown that U is contained in Fp. So we have used all the 4 conditions here to show that Fb contains a ball of, so Fb contains an open ball centered at Fa. We actually found a ball of radius m over 2, where m is the minimum of the function g. Okay, so this is, so what we have shown here is that you have a function f with non-zero Jacobian, and if you have an open ball, then the image of the open ball, the image of the open ball also has a ball centered at f of a, contains a ball centered at f of a. Now what we will do is that whatever we have done here for an open ball, this result, we are going to now do this for an open set. Okay, from open ball we are going to increment an open set. So what is the statement that we need to show? So now we have an open set. U is an open subset of Rn, and f is continuous in U. It's a vector valued function again. As again, all partial derivatives exist for all x in U. The third assumption is f is injective, right? This is replacing the condition that we had here, that fx is not equal to fa for all boundary, right? That is now replaced by f is injective, right? Which means that for distinct xy, f of x and f of y are distinct, right? Something very similar to earlier we had assumed that they are distinct on the boundary, right? The center and the boundary have distinct values. Now it's injective, right? Injective on y, and the Jacobian is the determinant of the Jacobian is non-zero, right? If all these 4 happens, then then the image of this open set is an open set in Rn. Okay, right? Is that fine? So you have a continuous function, other 3 conditions. So if you have an open set, then f of u is also an open set of Rn. So proof is simple in this case. We just reduce it to the uh, we just use the previous theorem. So you start with a y in f of u, right? Now if y is in f of u, that means there is some a in u, which means y is an image of some a in u under f. So y is f of a for some a. Now because u is open, and A is in U, there is a ball of radius R which is contained in U, right? Because U is open. Now, if you restrict F to this ball of radius RB, right, then that F will satisfy all the hypotheses of the theorem that we just proved for open ball, and the previous theorem that we proved. It will satisfy all the condition. So the injectivity on U is going to give you the third condition and the corresponding third condition in the previous theorem. Right? So if you restrict it to that ball of radius R, that F is going to satisfy all these conditions here. Right? If there is no issue with 1, there is no issue with 2, there is no issue with 4, because they are already there in the hypothesis of the new theorem. So only thing that you need to verify is this, and that will follow from the injectivity assumption of F on U. Okay. So from the previous theorem, we know that f of b contains an open ball centered at f of y, which is at y. F of a, f of a, which is y, right? Which means what we have shown is that we took a y, we have found an open ball centered at y. So which means that f of u is open. Fine. So we have shown that the image of open set is open set under these conditions. Okay. Now we are going to prove this result, that if you take an open set and if f is continuous, has continuous partial derivatives, something like previous theorem, and also the determinant of the Jacobian matrix is non-zero for some a in U. So here j of x is for all x in U, right? Here we are assuming it's non-zero for some a, then there exists an open ball centered uh, at A. So this A, right, whatever the A where the determinant is non-zero, there is an open ball centered at that A on which F is injected. Okay, so here we are kind of proving a more general result. Unlike here we had the assumption that F is injective. Now what we are saying is uh, we have an open set and we have F which admits continuous partial derivatives such that the Jacobian is non-zero at some point of the open set. Then you can find a neighborhood around, you can find a ball around that point on which F is injected. Okay, so the only property that we are using is that the determinant of the Jacobian matrix is non-zero at that point. If you have such a point, then in a neighborhood of that point, the function is injective. That's what it is saying. So how do you prove this? So to prove this, what you do, you set up, you take n copies of Rn. So that's like Rn square. Okay, and how do you define? So basically, if you choose n points and you use a subset of U is an open subset of Rn, right? So any element of U is an n tuple, right? So if you choose n different points in U, then one can associate that n different points to a vector of Rn square in the following way. That is, you just write down the tuple one after another. So you have x1, which is n tuple, which is here. x2 is another n tuple, which is here. x3 is another n tuple. So this together is so this entire thing is an n square tuple. So this is an element of sorry. So this is an element of Rn square. Okay. Now, what we know here is that so the first n component is the first is this element x1, x2 and so on. So we just have concatenated the n different vectors in U as one vector, and then we can get a one. So we have just concatenated so n different elements, n different vectors in U as one vector in Rn square. Okay. So now we define a real valued function h on any subset of Rn square, right, wherever it has to be defined, because if I take U, then if I concatenate all elements of U, then I'm going to get some subset of Rn square, right? I'm not going to get the entire Rn square. So let's say we define H on that subset. How do we define that? It is Hz is determinant of this matrix. So this is a real valued function, right? So this is a real valued function where it says it's defined a subset of Rn square, and the value it takes is determinant of this matrix. Note that this is not the Jacobian matrix, right? Because you see this, so in each, so this is a matrix which is the n cross n matrix, where in each row the evaluation point is different. So in the first row, the evaluation point is x1. In the second row, the evaluation point is x2, and so on. So h of z is this matrix. Okay, this is not the determinant of the Jacobian matrix, right? So Jacobian matrix, the evaluation is at the same point. Okay, here for each row, the evaluation point is changing. Okay, so that is h of z. Okay. Now this H is continuous because it is determinant of a matrix. Determinant is a polynomial, right? So it's a continuous thing, and we are given anyway that each partial derivative is also continuous, right? So there is no issue. So each dj, so we have that H is continuous on from whatever subset we have defined it. So some, right, I mean, the domain of H, it's continuous. Okay, it's some subset of Rn. Now you choose a point A. What is a point A? So for instance, you know that there is a point A on which this determinant is non-zero, right? For some A in U. So this A is in U, which means one can create, so one has this vector capital A, which is just concatenation of A n times. So A itself is an n tuple. So you put x1 equal to A, put x2 equal to A, x3 equal to A. Basically, you choose all xi's here to be A. So you will get A n square times, right? That is your capital A. So choose A to be Rn square such that xi is equal to A for all I, right? Now what is the value of H on this capital A? H at capital A is determinant of dj fi, where now instead of xi you will have A here, right? So now in all the rows you have the same element A because that is how you chose your A. So H of capital A is the determinant of the Jacobian matrix evaluated at A. Now that is given to be non-zero. So H of A is non-zero, right? So H is a continuous map and it is non-zero at the point A, non-zero at the point capital A. So by the continuity of H, there is an open ball. There is an open ball. There is an open ball omega centered at A belonging to Rn square, right? Thus by the continuity of H, we have an open ball centered at A such that H is non-zero for all elements in the open ball. Okay, because it's non-zero at one point, so there is a neighborhood in which it's non-zero by the continuity property. So omega is that neighborhood, that open ball, right? So therefore, determinant of dj fi xi is non-zero for all xi in this ball B. What is this B? So you see this omega is an open ball in Rn square, right? So this omega is an open ball in Rn square, and this omega is sitting in the domain of H. Okay, So the domain of H is obtained where every element can be seen as concatenation of n elements of U, right? So if this is non-zero, so if Hz is non-zero for all z in omega, more or less you can think of B as a projection of omega onto one piece of Rn, right? Rn square is n Cartesian product of Rn. So you can think of B as so if you kind of project omega to Rn, right? You will have a ball centered at A, right? Because omega is a ball centered at capital A, and the projection of A uh, to Rn is the little a. So when you take the projection of this, so you get some ball B here, right? So you get some open ball centered at A in Rn. So this is now in, so this omega is in Rn square, whereas this B is in Rn, okay? So you can get one such ball in Rn such that determinant of this thing is not zero for all xi in B, right? Because this happens for all z in omega. So now we wish to claim that on this is the ball that we require on which F is injected. So suppose F is not injective on B, then what can happen is that you can find two distinct points x and y, right, such that f of x is equal to f of y. If it is not injective, we are going to get a contradiction that this cannot happen. So now what you do, so you have 2 points on which f takes the same value. So B is an open ball, so you just take the line joining x and y, right? So the entire, so basically here I mean the interval, right? So here there is no interval because you are in Rn square, but when I say interval, I mean you take the line joining x and y with x and y as the endpoints. That's a line, right? That's an interval. Okay. Now what you do, because f is differentiable in U, I can restrict it to this line, which is contained in U. So by mean value theorem, if you apply the one dimensional, right, mean value. So if you apply the mean value theorem on this line, so there is an xi in this line joining x and y. There is some xi in this line joining x and y, such that fi of y is fi of x. So this I can do for each I. Okay, okay. This is by the mean value theorem, right? So I have just used the one dimensional mean value theorem here, which is why I have taken this line joining x and y. Okay. So since B is convex because it's an open ball, B is convex, so the entire line joining, all the points in the line joining x and y is going to lie in B. Therefore, this xi that we have obtained is also going to lie in B for all i's. Now, we have already chosen x and y such that x is not equal to y and f of x is equal to f of y, right? So if f of x is equal to f of y, that means fi of y is equal to fi of x, right? These are all components of this f, right? Fi's are components of this f. So when they are equal, that means each component is same. So this is actually 0, the way we have chosen x and y. So by the choice of x and y, this LHS here is actually 0, which means we have this scalar product is 0, right? So LH is 0 and we have this equation is precisely this equation because this happens for each I. So for each I this is 0, which is going to give you this equation, right? This is now a system of linear equations which is equal to 0, where the matrix involved is the Jacobian matrix that acting on y minus x is 0, but that is determinant is non-zero, right, which is going to give you that y is equal to x, but that's a contradiction because we started with y not equal to x, which means our assumption is wrong and f has to be injective on this ball B. Okay, so what we have shown is this result that whenever you take an open set and if there is which admits continuous partial derivatives, I mean, open set and a function on the open set which admits continuous partial derivatives, and if there is a point, some point A such that the Jacobian is non-zero, then in a ball centered at that point, the function is injective. So locally it's injective, locally it's invertible. That's what, right? Okay. Now what we are going to remark now is that we cannot replace the condition we had in the previous theorem assumption that this Jacobian, so determinant was non-zero. The determinant of the Jacobian matrix was non-zero for some A in U, right? Suppose we replace this sum A with all x. So for all elements in U, if it's non-zero, can we say that F is injective on U, right? See, what we said was it was injective in a ball containing A. So if suppose JF is non-zero at every element of U, that means for every element there is a ball where it is injective, right? That is true from the previous result. But from that can we conclude that F is actually injective on U, right? That is not true. This is a local property and this need not be true globally, right? That's so an example. So the injective property is a local property. For each, there is a ball around A where it's injective. But even if it happens for each point A, all these can't be put together, and one can't say it's injective in the entire U. For instance, these balls can intersect, and in the intersection, something else can happen, right? So, as an example, if you take the exponential function in the complex plane, right? So this is the complex exponential function. So if you take that function, right, this is not injective on C, right? We know that, right? This is not injective on C because it is periodic at 2 pi periods. If you add a 2 pi element, we have seen this earlier in the earlier part of the course. So this is not an injective function. We know, so it's not injective on C. But you can verify immediately that the Jacobian of this function is non-zero for all elements of C. Why is it? This just comes from the Cauchy-Riemann equation, right? Because Jacobian of x, which is the derivative, which is actually by the Cauchy-Riemann equation, is the derivative of f mod square, which is precisely this, which is non-zero for all z and C. Okay, so in this case, you have a function for which the Jacobian is non-zero for all elements in the domain, whereas the function is not injective. So that property that we proved in the previous theorem is a local property. It's injective in some ball. Now finally, using this, we are going to prove the open mapping theorem corresponding uh, a, to a function in the finite dimensional case where the function is not necessarily linear, right? In the previous lecture, we had done in a more general setup of Banach space the open mapping theorem. So let U be an open subset of Rn. Sorry. So if U be an open subset of Rn, and f is a function on U which has continuous partial derivatives, and the Jacobian of f is non-zero for all x in U, right? Then f is an open mapping. So what we can say when the Jacobian is non-zero for all x, we cannot talk about injectivity and so on, right? What we can say is that the map is an open map. That is, the image of every open subset is open in the range. So proof of that. So you'd start with any any open subset of U. So let's call it omega. We want to show that f of omega is open in Rn. So you take any y in f of omega. So if y is in f of omega, that means it's in the range of f under, it's in the range of f of omega. So there is an x in omega such that f of x is u. Now Jacobian of f, determinant of the Jacobian matrix corresponding to f is non-zero for all x. So in particular, it's non-zero for this x, which is in U, right? So j of x is non-zero, right? So now, therefore, by the previous theorem that we have shown, there is an open ball centered at x on which f is injective, right? Because this is the A that we so the A is x here, so right. So there is a ball around x, right, and this ball is right. There is a ball around x. So this y is I'm just denoting to show that this x depends on y. Okay. So the choice of x was depending on y. So x was the pre-image of y. So there is a ball around x, which is contained in omega, which is centered at x, and on which f is injected by the previous theorem that we showed. So now this uh, now if I restrict this f to this ball, right, then it satisfies all the hypotheses of theorem 54. Okay, what is this one, right? Because we just showed that is injective on that ball. So if you take u to be that ball, b, y, x, right, then all these assumptions are satisfied in that ball. So which means f of b is open subset of Rn, f of bx y or byx. Yeah. So by that theorem, f of byx is contained in f of omega is open. So this is an open set containing y. Okay. Now this you can do for every y in f of omega. So if you do this, you are going to get so for each y, you are going to get a ball corresponding to its pre-image. Okay. So if you take union over all these f of b y's, that's going to be f of omega, right? So f of omega is an arbitrary union of open sets and hence is open. So we need to show that f of omega is open. We have shown that f of omega is open because it's a union of arbitrary open sets, right, for all y, and each of them is open from the previous case. Okay, so which means that the image of every open set is open set. So this we have so here how did we prove the open map property of this function? The function just had to have continuous partial derivatives, and the determinant of the Jacobian matrix should be non-zero, right? That happens, then it's an open map. Okay, with this we will stop and we'll meet in the next lecture. In the next lecture, we will show probably the inverse function theorem and the implicit function theorem. Thanks a lot.